In this video, we're going to do some more complicated proofs about subspaces in vector spaces. So for the first one, we want to let H and K be subspaces of some vector space V, and we want to show that the intersection of H and K is also a subspace of V. So if we have a subspace H that looks like this, and say we have a subspace K that looks like this, then we want to show that the intersection of the two, which will be this little line here, is also a subspace. So visually, that's kind of what we're looking at. So there's three properties. The first property is we have to show that the zero vector is going to be in H intersection K. So, well, H and K are subspaces, so that means that the zero vector is going to be in H, and the zero vector is going to be in K, therefore the zero vector is going to be in the intersection. Since, if you may have forgotten, the intersection, so if I say x intersection y, this is the set of all x such that x is in big X and x is in big Y. So that is the intersection. It's going to be in both. Okay, so the zero vector is in both, therefore it's in the intersection. For 2, we want to show that if we have any two vectors, so let's say we have u and v in H intersection K, then we're going to have u plus v in H intersection K. So let's suppose we have vectors u and v in H intersection K. So then what we know is we know that u and v are going to be in H, and the vectors u and v are going to be in K, since by definition, if they're in the intersection, they're going to be in both. And because H and K are subspaces, if u is in H and v is in H, then we know that u plus v is going to be in H. And if u and v are in K, then u plus v are going to be in K. Therefore, u plus v is in H and u plus v is in K, so we're going to get u plus v is in the intersection of H and K. That's condition number 2. Okay, so condition number 3 says that if we have, say, some vector u in H intersection K, then we're also going to have any scalar c times u in H intersection K. Well, first thing we're going to do is we're going to assume we have this u in H intersection K, so this means that u is going to be in H, and u is going to be in K, because if it's in the intersection, it's going to be in both. And because H is a subspace, any scalar times u is going to be in H. Because K is a subspace, any scalar times u is going to be in K. Any scalar times u is in both of these, therefore C times u is going to be in the intersection of H and K. So, therefore we have proven that if H and K are subspaces, then H intersection K is also going to be a subspace. Okay, so that's the first proof. Second proof, a little bit easier. Suppose we have a scalar times u is equal to the zero vector for some non-zero scalar. We need to show that u is equal to the zero vector. I know, this seems really intuitive. So if I have like 3 times the vector u is equal to 0, obviously u is going to be 0. But let's prove that. So let's start with u. We should start with 1 times u. So maybe that'd be a little bit easier, because now we have this 1 here that we can work with. And what's nice about 1? Well, what's nice about 1 is that in algebra, if we have a number, say c, and we multiply it by its inverse, 1 times c, then we get 1 back. So we can change this 1 to be c times c inverse times u. Okay, so that's a really nice property of the number 1, is that 1 is equal to c times c inverse. And because c is non-zero, we can do this. Okay, so now the next step, we should flip these around for commutativity. So we're going to have c1 times c times the vector u, and then we should group up this c times u together. So why do we want to group up this c times u? Well, we do that because we suppose that c times u is equal to the zero vector. We're just trying to prove that u is equal to 0. So we know c times u is equal to the zero vector. Therefore, we know that this is going to be equivalent to the inverse of c times the 0 vector. So what's the nice thing about the 0 vector? Well, we know anything times the 0 vector is just going to be the 0 vector. Therefore, we have shown that u is equal to the 0 vector. Okay, so those are two proofs with subspaces. If you have any questions, please leave them in the comments below. Pretty much all of the practice videos for linear algebra are just going to be proofs like this, and I really hope they help because proofs in linear algebra are definitely harder than anything you've probably encountered before in mathematics if this is your first linear algebra course. So, any questions, comments below, and I'll answer them the best that I can.